Hello friends, I am Ashutosh Kumar from ZerOOne. Today we are here to discuss our topic on theory of computation, or somewhat known as automata theory. So, as you can see, the prerequisites that are elementary discrete math, notion of set, function, relation, product, partial order, equivalence and graphs, principle of mathematical induction. So these are the prerequisites that you must know before learning theory of computation. If you know this, well and good. If you do not know this, do not worry. Whenever we encounter, I will solve the problem for you and I will explain you the theory involved. Okay, so now let us jump to theory of computation. Okay, so when we deal with core computer science theory section, we encounter three theories. One is computability theory. Another is complexity theory. And third, the famous one, automata theory. Let us get a brief idea about these theories. So, computability theory tells whether a problem is computable or not. Okay, so this computability theory is going to tell you whether a given problem is computable or not. For now, just keep in mind this thing only. Okay, now complexity theory. When you read data structure or algorithm, you come through this theory. Okay, this complexity theory gives you the efficiency of an algorithm. You are able to compare between two algorithms, which algorithm is better than the other. So in short, we can say complexity theory are like space complexity theory and time complexity theory. This gives you comparison between two algorithms, that whose runtime is better or which algorithm is taking less space. So we have a trade-off, a space-time trade-off. So we shall discuss this topic complexity theory in algorithms. Now our main focus will be automata theory. Okay, in automata theory we have machine model. Okay, we have machine model to solve a class of problem. See, when I say that automata theory is about machine model to solve a class of problem, you might do not understand now. So do not worry, the today's whole lecture will be devoted to this automata theory only. Okay, so when we cover this whole lecture of this session, then we will come to know about the automata theory, and our focus is to automata theory only. Okay, now see guys, when we talk of theory of computation, as the name suggests, it is suggesting something that is computable. Okay, so when we talk about computing, what we think of, when we get a program, when we write a program, we are solving a problem or we are computing something. So whenever we talk about theory of computation, the first thing that strikes in our mind, the first thing that strikes in our intuitive mind, I might say, is that about programs. Okay, so whenever we talk of program, we talk of algorithms. Okay, so theory of computation or theory of computability, theory of computation. When we talk about theory of computation, this means in a way we are talking about theory of programs. Clear? And when we talk about theory of programs, directly or indirectly, we are talking about theory of algorithms. Okay, so this is the, in a way we are referencing theory of computation to theory of algorithm. So we will see how we will revert back from theory of algorithm to our main topic, theory of computation. So again, when we talk about computation, we think of programs, because using programs we solve certain problems, and whenever we talk about programs we think about algorithms. So then we need to know what are algorithms. Okay, so the most basic definition of algorithm is a finite set of steps which terminates. Okay, so algorithm is a finite set of steps which will terminate and will give you some solution. Now let us focus on its mathematical definition. Suppose we have a function. Okay, so what does a function does? It takes some input and gives you a output. Okay, also remember that the input that we provide are having input that we provide are constant to functions. Okay, means we cannot provide the input which we want. The functions will be able to accept, certain specific inputs only, and those inputs that we are able to provide to the function are known as domain, and this that domain will have a mapping to the range. Okay, so we have a mapping between domain and range. So if it is domain and this is range, so what a function does, function has a mapping from domain to range. So suppose if fa is a if I write fa equal to b, what does it mean? That this argument, when a is given to f, means when a is the input, the output is b. So a will fall under the domain set and b will fall under the range set. So what does algorithm does? Algorithm gives you a mechanism of mapping. Okay, so mathematically we can say that, let me write this term, algorithms gives you a mechanism of mapping from domain to range. Well, clear? So again, whenever we solve a problem, whatever target is that whenever we face problem, we design algorithm. Now designing algorithm or optimizing it is another issue. Here whatever focus will be, are we able to solve certain kind of problem? Are we able to develop a model which will solve a class of problem? Okay, so to deal with, let us see. Suppose if I write so this is a function. Okay, this is a function. So this is the function definition. What is the definition? That given an input to the function, the value will be x for a greater than 5, and given an input, the value will be equal to y for a less than 5. So this is the function definition. This is the function definition. Okay, now defining the function does not mean that we have solved the problem. So this is a very simple problem here, that we have to give input and we have to decide, okay, whether it is greater than 5 or less than 5. So the algorithm seems obvious here. There will be certain kind of problems where you can define a function and you cannot easily predict what may be the algorithm for that function. Okay, so surprisingly you might know that for most of the functions there do not exist any algorithm. Okay, so there are functions for which you cannot design algorithms, and the number are more, about 90%. See, I told you about functions and algorithms and relation between them. Okay, let us focus on this. Okay, so we have an input range, we have an output range, and there is a mapping. So what a algorithm will do, algorithm will carry a transformation. Okay, so algorithm is carrying transformation from input to output. Okay, so this was the idea that I gave you. And again, you can see an algorithm in this way also. Algorithm is taking an input and giving you output. So whatever intuition is, how we think intuitively is that for any input x, the output is fx. So there will be a function fx. Okay, there will be a function fx. So what our goal is, our goal is that for what function we can design algorithm. Suppose we have input x and we get some output. Okay, so can we design in any way that we develop a function for that algorithm? Are you getting my point? Or you can rather say that, can we develop an algorithm so that a function fx is computable? Okay, so which function can admit algorithm to compute them? So our goal in theory of computation will be in search of those functions which can admit algorithms to compute problem. Suppose the input is x and the output becomes to fx. So can we have algorithms which can admit to solve this function? Okay. So now, if there is a function mapping from domain to range, we can also have a graph. Okay, graph of function. See, this is a and b. So for f, and the input is a, the output is b. Okay, so we have 2 points. Okay, we have 2 points, a and b. Basically these are not 2 points, but these are two elements. Okay, these are two elements, a and b, which can form a point. Okay, which can form a point. Now we can have a graph for that function. So the concept of set membership problem comes. Okay, now let us realize what does the set membership problem actually mean. See, set membership problem, you ask problem to yourself. Suppose there is a set S on certain rule. Okay, there is set S on certain rule. On certain rule, I mean that an element will only be a member of a set S when it satisfies certain conditions. So ask whether A belongs to S, whether A belongs to S. So this is basically the set membership problem, whether a entity belongs to a set or not. So how we relate this to our function and algorithm notion? See, when we have a function, we have f, domain to range mapping, and then we can have a graph. Okay, we can have a graph of f, and what is that graph? Graph is a, b, such that f of a is b. Okay, so whenever we have a function, we can have a graph for that function. Suppose we have a function f x and it gives you some y, we can have a graph. So this ab belongs to a set of certain function. This ab belongs to a set of a certain function. So okay guys, my question is, which function can admit algorithm to compute them? Okay, so we are in search of those functions which can admit algorithm to compute them. Okay, so we will be searching those functions which can admit algorithm so that we are able to compute those. Okay, so this was the set membership problem. Okay, now let us proceed to some formal definitions, and when we advance in due course, we will see how this set membership problem is related to theory of computation, and we will have models, okay, that we will discuss at the end of this lecture. Okay, so let me define something on its symbol. and then alphabet, and then strings. Okay, before defining this thing, what an algorithm does, an algorithm takes input. So our input is generally strings, so it will produce some output string. So you can relate that we are giving some strings and the output will be string. We can form a graph. Okay, so we can relate to this. Okay, so whenever we talk about symbol, what does this mean? You know, symbol gives you an symbol gives you an intuition of stimulus. You know, whenever you see a symbol, you come to a intuitive idea. Okay, so symbol is nothing, you know, you cannot define symbol formally, but suppose 0, 1, a, b, what are those? Those are symbols. Okay, so these things are symbols. What are alphabet? So alphabets will be like, you know, collection of symbols. Alphabets are set of symbols, like when we say a to z. So this is an alphabet. What are strings? Strings are produced over an alphabet. Okay, so when we say we have an alphabet 0, 1, and then what will be the string? See, 0, 1, it can be a string, or 0 can be a string, or 1, 0 can be a string, or 0, 0, 1 can, infinitely many strings are possible over this alphabet. So this is string. Okay, now let us know about the notations. So this alphabet is denoted by sigma, and this string is denoted by sigma star. Okay, so we can have a binary alphabet, we can have an alphabet whose symbols are binary, like 0 and 1. So the sigma is, I can write sigma equals to 0. So what will be sigma star? Okay, so our focus is sigma star can contain infinitely many strings, but a single string must be finite. Okay, so sigma star can contain infinitely many strings, but a single string, a member of a single string which is a member of sigma star should be finite. You know, formally we do not have any upper bound, but we cannot have infinitely long string. Okay, because you are never gonna be able to input infinitely large string. Okay, so this is the notion of symbol, alphabet, and a string. Let us see the concept of formal language. What formal language mean? We say a formal language L over an alphabet sigma is a subset of sigma star. Okay, so a formal language L is a subset of sigma star over an alphabet sigma. For example, if sigma is an alphabet, over symbol 0, 1, then L equals to 0, 1, 1, 0, 0, 0, 1, 0. Say for example, this subset of sigma star. So this L is a formal language over this alphabet sigma, and it will be a subset of sigma star. So let us formalize this definition in a more strict way. Okay, if we say sigma is 0 1 and we define a language L1 and we say that it consists of even number of zeros. Okay, we say that this language will consist of strings where the number of zeros will be even. So this L1 will be like this 0 0 or 0 0 1, or it can be 1 0 0 this way. So this set will be infinite, but see, this single entity will be finite. And what is the constraint? That the number of zeros is even. So we can say that L1 is a proper subset of sigma star. Okay, by proper subset, what we mean that every element of L1 is in sigma star. Okay, but the every element of sigma star is not in L1. Okay, if we say A is a proper subset of B, then there must be some elements in B which will not be in A. Okay, so this was the formal language. So guys, we discussed a lot about algorithm, functions and set membership problem. Why we discussed all those was just to realize what actually theory of computation is, what actually automata is, what this mean. Okay, so to summarize, we can have an idea. Okay, then what we were talking about that is, for a function, for a class of functions, are there such functions which will admit to an algorithm? Isn't it? We discussed that functions are there some functions which will admit to an algorithm so that the function become computable. So this was what when we discussed about function, and we related function to algorithm. Again we related function to set membership problem. Isn't it? We related function to set membership problem. How? So for every function f, if it takes the input, the argument, it gives an output. So we can think of a graph. So we will have a set, a b, or suppose x y, such that this x and y, when x is here, y is here, so that the relationship is satisfied. So what we did, we had algorithm, and we saw a formal relationship between algorithm and functions, and then we saw a relationship between function and set membership problem. And whatever goal was to find functions which can admit an algorithm to compute them. Okay, now we invert this idea. We are inverting this idea. How we are inverting this idea? See, what we do, we are inverting the idea that can we have a model of computation which will admit some set of problems? Can we have model of computations? What we were previously thinking about, we were thinking about of functions that can admit to algorithm. Okay, now we are thinking about, can we have any such model of computation? So can we have a model of computation so that some class of problem is computable? Okay, so this concept will be clear when we advance in our lecture, but for now our target was about realizing the concept of set membership problem. Now this is what we call automaton or automator. Okay, so the question is, can we have model of computation? So this is a bit, now it may sound a bit difficult, but when we advance we will see what are the model. So just to give a glimpse of what we will be covering in our next sections, the model of computations that we have are finite state model, and then push down automata, and the famous Turing machine. Okay, so these are the models. So automata is basically dealing with the models that will solve certain class of problem. So do not get confused now. We will see how these models will work and what automata is all about. But for now, I believe that you got an understanding what theory of computation or what the theory of automata will deal with. It will deal with certain inputs, giving some output. Okay, and that input output relationship will be mapped by algorithm, and we focus to find a class of problems that can admit algorithm. Okay, so what is we have finite state model. So this is a machine model. We will see there are various kinds under this section. Again we have push down automata. Under this also we have certain class of problems, and this is the famous one. This actually deals with which kind of problem can be solved or not. In the due course of sections, we will also learn several concepts like grammar, okay, regular languages, regular expression, pumping lemma, these things we will learn. These things we are going to learn when we study these models of computation. Okay, so for now guys, I think it is enough to have a very basic and brief idea about what theory of computation is all about. And believe me, whenever we start studying theory of computation in automata, we just jump on finite state models, we draw those state transition diagrams without realizing what our aim is to. And every time I say, whenever we study a subject, we should first focus that what this subject is dealing with and why should we study it, where our goal is, and what we are trying to do when we study some concept. Okay guys, thank you for watching this video. I hope you have liked it. Please like and subscribe our channel ZerOOne.